The Transportation Security Administration, or TSA scenario, is obviously an MM1 model queuing theory problem. What might not be so obvious about it is that it's not actually one MM1 problem, it's 30 MM1 problems. Now let me show you what I mean. The U.S. Transportation Security Administration, TSA, operates six checkpoints for screening departing passengers at the Buffalo Niagara International Airport. Each checkpoint consists of a baggage conveyor belt, CTX scanning imaging machine, and walk-through metal detectors for passengers, although all 6 checkpoints are not necessarily operating all the time. This is because each checkpoint requires a team of 3 TSA employees to staff it, and there's not always a need to have all 6 checkpoints running simultaneously. Passengers arriving at the airport are first met by a greeter who directs each passenger to one particular checkpoint that is in operation at that moment. Now, before we go any further, I just want to do a little sketch so far. So we're saying that there's this mysterious source of customer arrivals. It's people arriving at the airport, like little circles are meant to be the people, and they start showing up. There is somebody called a greeter who meets them as they're coming in the door and directs them to one of, can I draw 6 of these and still make them fit in here? One of 6 so-called checkpoints, which are essentially each one of them a service system. Right, like, oh, you could go here, okay, and then they get in line here, or you could go, the greeter say, go over here, this one's open, okay, fine, and then a line forms. This one. So right away, we don't have one queuing problem. You say, well, there's 6 checkpoints. There may be like upwards of, they don't always have them open all the time. There may be upwards of sort of 6 little queuing problems going here, right? You said 30. Where do you get 30? That comes in the later information. Once greeted, each passenger then joins an assigned checkpoint single line. Okay. And it takes an average of, now that is an important piece of information, it takes an average of 1 minute to actually screen each passenger through a checkpoint. So each checkpoint is a serviced system. That implies that each one of them is working at a certain rate. The abbreviation for that rate in the MM1 model is mu. It's going to be the same for each one of them. And we have this fact, an average of 1 per minute, or take an average, basically an average each minute. We don't want to write 1 here though, because that's a length, an average of 1 minute. And I notice over here there's a table about arrivals and hours. So before we even get there, I am writing an additional note to myself. Okay, there's this system. Maybe all these lanes are open, maybe they're not. When they are open, each one of them is running at a rate of mu equals 60 per hour. Because if it takes an average of 1 minute to screen a passenger, that means you can screen on average 60 an hour. Oh, all right, now, wait, we gotta keep going. The greeter's job is to divide the arriving passengers evenly between the checkpoints in operation, although the rate at which passengers arrive at the airport and approach the greeter varies throughout the time of day. So you can see that here at the beginning of the morning, from essentially 5 a.m. to 6 a.m., people are arriving at the airport at a rate of 100 an hour, and then it picks up. So there's this busy time from 6 to 8 a.m. That must be mostly departing flights, right? And then it gets a little quiet in the middle of the day, 8 to 4, but then there's this evening rush here where it picks up again, 290 passengers on average arriving in an hour. And then there's this really quiet period right at the end of the evening where it drops down to an average of about 50 people an hour, and that's just for what it says from 7 to 10 p.m. Okay, fine. Now this has got to have something to do with, if this is a queuing theory problem, what's lambda? What's the mean of the customer arrival distribution? Well, I've just been quoted a whole bunch of them. There's the 30 different problems. 6 different lanes. Each one of them is a queue. 5 different potential levels of customer arrivals. 5 times 6, there's 30 little problems embedded in here. Oh, all right, now, whoa. What are the actual questions? What is it that we have to do? Let's see. It says TSA must maintain enough checkpoints such that the average delay experienced at a checkpoint screening is less than 10 minutes. Okay, 10 minutes. I'm just taking notes. Something has to stay less than 10 minutes. What has to stay less than 10 minutes? The average delay experienced at a checkpoint screening. In the MM1 model, W is overall wait time, overall delay, and what that was just described there is W sub S. The average wait in the system, the average total amount of time it takes to clear the system, including waiting for service and actually being served. Oh, so this is what TSA is specifying. This is what will make TSA happy, right? If W sub S is less than 10 minutes. That's what they just said. All right, now I just noted it, really. We haven't decided anything or calculated anything. Okay. What do we actually have to do in this problem? Recommend the number of checkpoints the TSA should operate during the various time intervals of day described by the table above, meaning the page before in the case of the note frame, keeping in mind that TSA would prefer to minimize the staffing required. Oh, all right. So for each of these major time periods, we're to find out how many checkpoints TSA should have open. You say, well, how are we supposed to decide how many they want to have open? WS less than, I should say less than 10 minutes, so that the overall delay, that's what will make them happy, is less than 10 minutes. Now there is in the note frame this overall blank frame. So you can see, right, here's the time periods. We have to come up with a recommended number of checkpoints, bearing in mind that they'd like to open as few checkpoints as possible, given they can keep the wait under 10 minutes. All right, so this is just copy paste again. That's the data on customer arrival, and there are these 6 blank columns. Yes, I'm going to write lanes for checkpoint lanes. We have to investigate having 1 open, 2 open, 3, 4, 5, and 6 open. So each square in this table is a potential scenario. For instance, right here, oh, that is the staffing where you have 2 lanes open at, what's the row between 6 a.m. and 8 a.m. Would we want to do that, or would we want to do this? So that's where you have 4 lanes open right here between 8 a.m. and in 4 p.m. Would we want to do that? I don't know yet what we should want to do, but there is something we should note. It doesn't matter, any one of these, mu equals 60 per hour. Okay, each lane will be working at that. One thing we need to realize, though, is this combination of the actual arrival level at the airport and the number of lanes is changing lambda. And that is the key to this problem. Because what's the most obvious case? Oh, the most obvious case. Let us suppose that we decide to have 1 checkpoint lane open from 5 a.m. to 6 a.m. Well, it says that the average number of passengers arriving at the airport is 100 per hour. That means that, lambda would equal 100 per hour. Now, if we decide to open 2 lanes in this particular time interval, the greeter is going to split that arriving traffic evenly. That's what the scenario told us. That means effectively for each lane, lambda is 50 per hour. Oh, and then if we decide to open 3 lanes for each lane, the average number of people that would be arriving at that lane and joining the queue is, was at 33.33 versus, let's see, 100 divided by 4 is 25. Lambda equal 25 if it's 4 lanes. Lambda equal 20 per hour if it's 5 lanes. And lambda equals, let's see, what is that? 100 divided by 6. Oh, little messy, 16.67 people per hour. now you say, okay, so I have all these different lambdas. Yes, and you're going to need them because we are going to need to figure out what the actual weight would be in each case, and we need lambda and we need mu. Mu will always be the same. Lambda is the one that varies. All right, now first maybe what we ought to do, just to stay organized, is go ahead and populate this table, so to speak. We're going to need to know this. Let's go ahead and figure out what the lambda would be in all these cases. So from 6 a.m. to 8 a.m., if you only have one lane open, then at that lane, the passengers are going to arrive at a rate of 290 an hour. If you have two lanes open, you will be splitting that traffic. So lambda equals, what's that, 145? If you have three lanes open, it will be 290 divided by 3. I get, okay, that is an average of 96.67 passengers arriving at each checkpoint lane. If you open 4 lanes, 290 divided by 4, I get 72.5. If you have 5 lanes, 290 divided by 5, I get 58, an average of 58 passengers arriving in each lane. And then 290 divided by 6, I get 48.33. And something nice here, notice that this arrival rate for 6 a.m. to 8 a.m. is the same thing as from 4 p.m. to 7 p.m. That means I can just copy my work on this row also. 290, 145, 96.67, 72.5, 58, and all 6 checkpoints open means that each one an average of 48.33 passengers an hour. All right, now we have to do the center row. If you only have one lane open in the middle of the day, then all 180 people on average will arrive each hour at that lane. If you have 2 lanes open, the greeter will split them, and so an average of 90 passengers will arrive in each lane. If you have 3 lanes open, the greeter will split them at 180 divided by 3, an average of 60 passengers per lane. Lambda with 4 lanes, 180 divided by 4, I get 45. Then 180 divided by 5, if there were 5 lanes, would be 36. And then finally, if there were 6 lanes open, that would be an average of 30 passengers an hour at each lane. And then finally down here, lambda equal 50 if you only have 1. Split it, 25 if you have 2. Lambda equal 50 divided by 3, 16.67 passengers an hour if you have 3 lanes. Or lambda equal 12.5 if you have 4 lanes. Or lambda equal an average of 10 passengers an hour if you have 5 lanes. Or lambda equal an average of only 8 1/3 passengers arriving each hour at each checkpoint if you've got all 6 checkpoints open right at the end of the day when there's hardly any passengers arriving at the airport. Oh, all right. Now, looks like we have what we need to, right, you know, what we would say, all right, for each one of these intervals, what number of lanes are we sure that WS is less than or equal to? Now I want to write 10 minutes. Well, I will. I'll write 10 minutes. Although one thing I need to remember is the M1 formulas, if lambda and mu are in hours, and they are, they want to report back in hours, so it might be a good time to translate 10 minutes into hours, which is 10 out of 60, or, well, 10 minutes is 1/6 of an hour. Okay, so I want to check, in fact, for a certain number of lanes, if in fact the weight is, once the overall delay is 1/6 of an hour. Now you might be thinking, oh goodness, I'm looking at the formula sheet and I'm thinking we're going to have to do that 30 times. Well, actually, no. No, not if you're alert. First off, there's some easy cutting here. What do I mean by cutting? there's a bunch of scenarios or squares in this table that once you look at them now, they don't make any sense. There's no point in calculating the average delay because that would never work anyway. Why is that? This is never going to work. The system is never going to work unless, and the MM1 model assumes that mu is greater than lambda. Mu is the service rate, lambda is the arrival rate. The whole MM1 model and all of those formulas don't work unless the service rate's faster than the arrival rate. If the service rate's not faster than the arrival rate, you have a system that will never keep up anyway, so why bother calculating the length of the line because it will be endlessly exploding anyway. Look at, for example, first thing in the morning, if we open only one lane, people are going to arrive at an average of 100 an hour. We can only process them at a rate of 60 an hour. That's never going to work. There's no point in plugging those parameters into any formula. You can just throw that out. That's sort of it's what we say is not feasible. Okay, there's no need to investigate if the wait will be less than 10 minutes. It would never work to start with. Likewise, look at, for instance, actually more dramatic, look at, for instance, from 6 a.m. to 8 a.m. Okay, if we open only one lane during that busy time, we will have 290 passengers on average in an hour. If we have only one lane, that lane is only working at a rate of 60 passengers an hour. That will never work. We need a lambda that's smaller than 60. None of these numbers will work. We don't, in the case of the busy period from 6 a.m. to 8 a.m., we don't get into a situation that might work maybe, we just don't know what the delay is, until you've opened at least 5 lanes. Oh, so we know that we don't have to start working until right there. Let's see, in the case of 8 a.m. to 4 p.m., none of those will work. It's interesting, right here, if you open 3 lanes, lambda is exactly 60. It exactly matches mu. You know, that's not going to work either. Sounds like it would be nice. But mu really needs to be bigger than lambda. Okay, so I know I don't need to look at those. This is the same business about the 290. None of those scenarios make any sense. Down here already, 50, 60. I can't throw out any of those. Okay, they would all work for us. The issue is just now that delay. Is the delay less than 10 minutes? Oh, so you say, okay, fine. I don't have to work the formulas 30 times. I only have to work them like all of these other, the ones that are open, like for half, however many those are. And the answer is yes, if you want to work it that way. You need to start checking these, each one of these scenarios. But here's what you do. You start with the smallest number of lanes that's feasible, that will work, and check it. Compute W sub S, the average delay in the system, and if it's less than 10 minutes, that's the answer for that particular time interval. Perfect. You don't need to go any further. If it fails that, you got to keep checking the next number and then the next number and the next number. Like, as an example, if you wanted to do it that way, now notice I said if you want to do it that way, you would just have to start somewhere. You could start right here. As an example. Oh, okay. And you know, it's going to be a lot of scratch work here. I better make some notes. What I am looking at is the 5 a.m. to 6 a.m. And what I'm looking at is 2 lanes. You know, that's really actually the name of the scenario. Okay, because that means that lambda equals 50 and mu equals 60, and I need to calculate this. Oh, so I need a formula sheet. Okay. Well, luckily with the no frames, there's a formula sheet. So I need to compute, I need to calculate, I need to use that formula right there, W sub S, with lambda equal 50 and mu equal 60. Oh, but wait a minute, that formula, I'll copy it here. We're just working on, remember, we're just working on this one square right here, right? WS equals WQ plus 1 over mu. I need the formula for WQ to do this. Yes, you do. All right, WQ equals LQ. Oops, that's supposed to be a Q. Divided by lambda. Well, to fill this out, I need the formula. Yes, you do. For LQ, the average length of the line, that is lambda squared over mu minus lambda. Now remember, we're still just evaluating 5 a.m. to 6 a.m. With 2 lanes open. And we need all 3 of these formulas to do that. Because we're going to have to start actually at the bottom of the list, fill that in, and then substitute it up. So if we were to do it that way, might as well. Let me fill that in. Okay, so just this scenario, that would be 50 squared over 60 times 60 minus 50. I get on my calculator 4.1667. It's repeating. Oh, okay, so if we had 2 lanes open between 5 and 6 a.m., we'd have about 4 people in line in front of it. That's actually what that formula means. Now, if you put that in your calculator and you're looking at this number, just keep that number and then say we're substituting it in up here, 4.1667 divided by lambda. Remember, lambda is 50. I did that and I saw 0.08333. Right, that is the average weight in the queue. Remember, that's in hours. Now store that number because, right, we need that number for here because it's 0.0833 plus 1 over 60. Store that number, divide 60 into 1, add them together, and you'll get 0.1, essentially. You say, oh, phew. Okay, that's the average delay. Is that good enough for TSA? Well, it's 0.1 hours. Oh, well, what did they say? They said they want it to be less than 10 minutes. Oh, okay, 0.1 hours, 0.1 times 60 converts it into minutes. That is an average overall delay of 6 minutes. Perfect, 6 minutes is less than 10. I have confirmed actually that 2 lanes, at least between 5 and 6 a.m., 2 lanes would be good enough. There's no need, happy news in this case, to investigate 3 lanes, 4 lanes, or 5 lanes, right? We would just expect there'd be a shorter wait, but this wait's good enough. We're trying to minimize lanes. Now, we still have like a lot of work to do, right? Because you'd have to check here, and you have to check here, and if any of these fail, you have to keep checking. Okay, we actually, and all that scratch work each time, we actually didn't need to do any of that. There actually is a much faster way to do this. You say, oh, now you tell me. As long as you invest some time up front in careful manipulation of the algebra of the MM1 model. You say, huh? Okay, I'm going to show you. You can do it. Now, this, if you understand this, you can picture this, then, especially if you're maybe working in a spreadsheet where you can copy the formulas, do it this way. But I did want to show you that there's a much faster way to do this if you're just will get comfortable with the algebra of the model. Because this is the MM1 model, right? That's what I was pointing at here. This is the formula that we're interested in particular, W sub S. Oh, now, the other way to do it, just logic, really. You say, okay, TSA says they will be happy if W sub S is less than 10 minutes, or as we were remarking, that is 1/6 of an hour. Okay, this will make them happy. Now, this W sub S, I'm just looking at the formula sheet, is W sub Q plus 1 over mu. I'm going to substitute that in. That's all I'm doing. WQ plus 1 over mu. The rest of this doesn't change. They'll be happy if that is less than 1/6. Okay, now wait, WQ, you can see from the formula sheet, is LQ over lambda. Okay, I am going to substitute that in here. For WQ, instead I'm going to write LQ divided by lambda. The rest of it doesn't change, plus 1 over mu. They'll be happy if that is less than 1/6. Oh, wait, right, and LQ by itself is a formula. You see it right here. I'm going to substitute it in. Now, it is a rather complex formula by itself. It is lambda squared divided by mu minus lambda. Now, to substitute it in, I need to then divide it by lambda, and I could write yet another line and say divided by lambda. That's going to get really messy and confusing. This is the same thing. Okay? LQ divided by lambda is the same thing as LQ times 1 over lambda. And this is just neater and tidier. The rest of this did not change. And then I realized that this will tidy up because lambda will cancel out. Here and there, there'll be a lambda left in the numerator over mu minus lambda, but that goes away. That's nice. And we still have this plus mu over here. Still, this hasn't changed. They would like to see that less than 1/6. And then I realized, wait a minute. Speaking of substituting, we're talking about what will make TSA happy. Well, TSA, we know something about mu. Mu is 60. We know this. So I could substitute in 60 here. Why don't I do that? I'm going to go back up here, just carefully. I'm just recopying it. Lambda over 60. 60 minus mu plus 1 over 60 less than or equal to 1/6. That would make them happy. Oh, okay. Now I can make this neater because I can subtract out 1/60th from each side. So this doesn't change over here. Lambda over 60 times 60 minus lambda less than, okay, 1/6 is 10/60ths. You know, check me on that. Subtract out 1/60th from each side, you're going to get 9/60ths left over. And then, oh, cool, wait a minute. I can make the two 60s go away. I can multiply both sides by 60. So this just becomes lambda over plain old 60 minus lambda. And over here, stops being a fraction. It's 9. Oh, okay, and then lambda less than or equal to 60 times 9 is 540 minus 9 lambda, right? I just multiplied both sides by 60 minus lambda. All right, now actually I can get the lambdas together. I can add 9 lambda to each side so that this becomes 10 lambda less than 540. Oh wait, which means lambda less than 54. I just solved that whole part B, basically, without having to actually substitute in any lambdas and mu's and calculate any wait times. You know, you say, well, I don't get it. You just have this thing that you boxed and it says lambda less than 54. Yes. TSA will be happy. The 10-minute, less than 10-minute delay will be met as long as lambda, the resulting lambda from the lane number choice decision, as long as lambda is less than 54. Oh, so to solve part B, instead of all this scratch work to check the actual times, I just look at, right, like for instance, this 50 is less than 54. Perfect, keep it. That's a keeper. Maybe I'll box them in green. We definitely do want 2 lanes open from 5 a.m. to 6 a.m. Here, I'm looking from 6 a.m. to 8 a.m. If we have 5 lanes open, the resulting lambda is 58. That is not less than 54, so that won't work. This is what we have to do. We have to open 6 lanes in order to drop lambda down low enough. Here, 45 is the first time lambda is low enough. It's associated with 4 lanes. Okay, perfect. That's the answer. Then again, in the evening, same business. Got to go back up to 6 lanes. And then, this little nighttime slot, 1 lane will do it. The resulting lambda equal 50 is less than 54. Right, that's my test. What I actually just figured out was the test for what would work. And then I don't actually have to calculate any wait times. So, to answer this question, what we just did, I boxed it in green. It says recommend the number of checkpoints they should keep open. My recommendation is from 5 to 6 a.m. 2, and then from 6 to 8 a.m. 6, and then from the middle of the day 8 a.m. to 4 p.m. 4, right? And then back out to 6 for the busy time, and then drop down to 1 for the end of the day. Done. Okay, done with that part of the problem. This is our plan. The other part of the problem asks us to evaluate our plan. Just when you thought you were done. Based on your recommendation, what is the average length of the line in front of the passenger checkpoint throughout the day? Oh, all right. Now, see the empty frame here? It's just meant to help us stay organized. Number of checkpoints or lanes. We've decided that. It's now 2, then 6, then 4, then 6, then 1. That's what we've decided. It's now asking what's the average length of the line in front of each checkpoint throughout the day. That is LQ, right? Remember, what was it? LQ equals lambda squared over mu minus lambda. So, for instance, in the case of right here, 5 a.m. to 6 a.m., we would have to solve that expression with mu equals 60 and lambda equal 50 because we have 2 checkpoints open, so the resulting lambda would be 50. And we did that in the scratch work before. Remember, that was the 4.1667? And then, oh, the ironic thing is, might as well take advantage of it. Look at the end of the day. We'll only have 1 checkpoint open, but the resulting lambda will be the same. That means I can just copy that number down. Yeah, there'll be about 4 people in front of the checkpoint on average then too. All right, so to answer this, we need to fill these other ones in. I get that as a result of 6 checkpoints being open during the busy times, when there's 290 people on average arriving at the airport, that the average length of the line will be 3.337, and it would be the same for both of these intervals, versus right in the middle of the day, the LQ that I get is 2.25. Again, by filling out that formula, mu equals 60, and in the case of the middle of the day, lambda equals 180 divided by 4. All right. Oh, okay. Now, it asks something else. It's like a tag on. During what time of the day is a passenger least likely to have to wait to be screened after talking to the greeter? Meaning that, you know, that they could just walk up and be screened. There isn't anybody in front of them. Oh, likelihood or probability, likelihood, that was what I was trying to write, of having to wait. This is not TSA, this is any MM1 problem. The probability of the likelihood of having to wait is actually really easy to calculate in any case. That is lambda over mu. You can look on the formula sheet. It says lambda over mu is labeled system utilization. Yes, that's the formal term for it, but it is the chance that you'd have to wait. Okay, because it's the percent of the time that the system's busy. If the system's busy, you have to wait. Oh, all right, so we could just calculate then that for each one of these intervals. Again, with the proper lambda, what I get here, you know, 50 divided by 60, 5 a.m. to 6 a.m., 0.833, or 83% probability you have to wait. That would be the same probability as down here, because it's the same lambda equals 50, and mu equals 60. So at the beginning and the end of the day, there's about an 83% chance you'll have to wait. It asks what time of the day is it least likely you'll have to wait. Okay, well then we can fill in the other ones. My calculations don't show that 6 a.m. to 8 a.m. is too terribly different. I mean, you do say 48.33, that's the lambda divided by 60, right? And like for 0.805, which is basically like 81%. There's a slightly, and this would be the same down here, there's a slightly smaller chance during those peak periods where all 6 lanes are open that you would have to wait. In the middle of the day, when lambda is 45, because it's 180 divided by 4 divided by 60, I get there's a 75% chance. 75% chance that you'd have to wait. Each lane is 75% utilized. All right, now, what did the question ask? It says, when is it least likely you'd have to wait? It's that long middle of the day part when they have 4 lanes open. Okay, so here's the average length of the line throughout the day, and least likely to wait from 8 a.m. to, what is that, 4 p.m.? That whole middle part of the day.